Hey, welcome to class. We are talking about measures of variation today. So there's two things when you have a set of data that you're interested in, maybe more than that, but two potentially on the front end is where is the middle of the data? So then that's what we talked about last time is measures of central tendency. Mean, median, mode tell you where the bulk of the information is, where's the middle, kind of a typical response. And then the second thing is measures of variation. What measures of variation tell you is how spread out the data is. Because you could have a middle and all of your data could be clustered right around that middle, or you could have a middle and there's a bunch of data way out here and way out here. And those are two very different scenarios. So understanding how spread out the data is pretty important in understanding what's happening with the data. So two things we're going to talk about, two of the main things we're going to talk about today. One's a review, one is the range. We talked about this when we did histograms, but the range is the largest number, or we call that the max, minus the minimum number. Okay, that tells you the endpoints. The problem with the range is it only uses those two endpoints. So it doesn't give us any information about in between. So if you think about it, like if your endpoints are here, all the data could be clustered around those endpoints and nothing could be in the middle, or these could be two outliers and all your data could be packed in here in the middle. And there's no way to know those two data sets would have the same range. So it's not an ideal measurement, but it is one that's there for variation. The other one is what we call standard deviation. And the standard deviation uses a pretty complicated formula that we're not really going to go into the mechanics of the math in it. But the way you calculate standard deviation involves all of the data values. So standard deviation will kick out a number, and that number is going to tell you roughly how spread out the values are, and it's more of an accurate reading than the range because it's using all the data values in the formula, whereas the range is only using the min and the max. So we'll just say for our purposes, standard deviation tells you how spread out the data is. Okay, real quick, I want to show you how to calculate it on your calculator, and then we'll look at some pictures and kind of get a feel for what we're talking about. So on the TI, you're going to go to stat. It's what we did last class period. So reference maybe the video for 2-3 if you're not sure how to do this, but you're going to hit your stat button, and then you're going to go calculate. And then you're picking one var stat. And in that long list of things we talked about last time, mean, median, mode, there's standard deviation in there, okay? On class calc, it's where we were the other day as well. If you hit stat, you've got standard deviation right here, okay? So it's the same calculator work that we did in section 2-3 on measures of central tendency, if you need to look back and need a visual for that. I want to take a minute and go over some notation. We did that a little last time, but I'm going to put it all here. So if you have a separate sheet of paper for your notation, which I strongly suggest, maybe get that out and let's add to it. So we talked about this is the mean. We talked about it yesterday, last class period, in terms of a sample. And that's what this is. It's the mean of a sample. And we say it's X bar. That's how we say that. And we also talked about N being the number of data entries. And then what we're going to talk about today is S, or your calculator sometimes writes S sub X. This is the standard deviation of a sample. Okay. Now, what if we're not looking at a sample? What if we're looking at a population? Then we use different letters, okay? So if we are looking at the mean of a population, we use this, it's a mu. I think you spell it M-U, maybe, mu. And it's a U with a tail on the front end. It's a Greek letter. And this is the mean of a population. So these guys are related. One's for a sample, one's for a population. And because we have different notation for it, we're able to delineate just from the notation what we're talking about. Are we in a sample or a population? Sorry, I was going to sneeze. Woo. The number of data entries in a sample is N, but if you are in a population, you use capital N. So this is in a population and this one's in a sample. And for standard deviation, we have the same thing too. For S is the standard deviation of a sample, but we use this sigma. So it kind of goes like this. You start here, you go around, and it's got like a flat top. That's how you write that. That's also a Greek letter. This is the standard deviation of a population. So when you're doing a problem, the first thing that you need to do is read the context of the problem and decide if it's a population or a sample. And then that dictates what notation you're going to use. In addition, your calculator is going to kick out a value that they are going to call S sub X. And they're also going to kick out a value for standard deviation that they're going to call sigma sub X. And you have to choose which number they're different because standard deviation, the way the equation works is for a sample, they're using this small n, they're using the number of data points for a sample, but for a population, they're using capital N, the number of points for a population. And so the numbers come out a little bit differently. So you need to make sure that you're picking the correct one. Okay, so as an example, let me go over here. I've got this data set above here. I called it A, so it's a huge data set. If I'm going to calculate, I'm going to go stat and I'm going to hit standard deviation right here. Standard deviation of list A. Do you see that there's two options there? One is my sigma value and one is my S value. So I'm going to choose this S value if it's a sample, and I'm going to choose this sigma value if it's a population. And you have to read the context of the problem to know. And on the TI, it's the same. It kicks out that long list of numbers. There's an S value and there's a sigma value, and you choose which one is appropriate for your problem. There's also two more things that are referenced. We talk about S squared. This is what we call the variance. And it's just the standard deviation squared. We are not going to use this a lot in our course. So I'm not going to spend a lot of time talking about it, but it does come up from time to time in the homework. So if it says variance, all you're going to do is just square the number that you have in as your standard deviation. Okay. It's also a measure of distribution. And then similarly, we've got sigma squared. This is the variance for the population. S squared is for your sample. Okay, so I think that is all the notation that you'll need for now. Keep track of that so that when it says find X bar, you understand what that means and what they're asking for. Okay, now let's look at a picture of standard deviations. Let's see, where did my pictures go? Hold on, here I pasted them on the wrong page. Okay, this is kind of going to give you an idea of what the numbers mean, okay? As you see in this picture, this is a histogram. So this picture right here is the data set is all fives. There's 8 fives. So this data set is 5, 5, 5, 5, right? 8 of them. because this is telling me how many there are, and this is telling me the actual data entry. So I've got 8 5s. So that histogram is just one bar. The mean obviously is 5, right? That's the middle. The standard deviation right here is 0 because it's not spread out at all. They're all one value, okay? Now, when I get a data value here, what this is saying is that I've got 1 3, I've got 2 4s, I've got 4 5s, 2 6s, and 1 7. All right, so you can see that that data set is symmetric, right? It's even on either side. The mean is still 5 because that's definitely the middle of that stack of data, but the standard deviation now is 1.2. So you kind of get a feel for like, okay, the range of this data is from 3 to 7, and that's going to give you roughly, like if it's symmetric, a standard deviation of 1.2. Over here, we have a set of data that it's also symmetric, but it's not bell shape. Okay, so it's spread out even more. Notice that most of your data is on the ends here and not in the middle. So that produces more weight on the edges, so that we would call that more spread out. And so the standard deviation is 3. So it kind of gives you a feel for, how that number, what that number means. If you had a standard deviation of like 12, that would be quite a bit more spread, and probably that means the data values are spread out as well. So that just gives you a visual for that. The next topic in this section is called the empirical rule. We're going to start by looking at a set of data that is symmetric and bell-shaped. Most of what we look at for the rest of the course is going to be distributed this way. There's some really interesting things about this kind of a distribution, and it actually happens more often than you'd think that data is shaped this way. So if you imagine, this has very few data points in this graph right here. We've only got 2, 4, 5, 6, 7, 8, 9. There's only 10 data points in this histogram, but I want you to imagine if we had like 100 data points in this distribution, and it was quite extensive. We would be drawing little bars forever, and they would be very high. It would just be a much more massive graph. And so what we do in statistics is, in a sense, we kind of shorthand this histogram, and we end up just drawing a smooth curve in a bell shape. And it looks kind of like this. So you're going to see this shape a lot. And what I want you to understand about this shape is that really it's a histogram, okay? It's just that we've smoothed out the edges of the bars. We're not drawing each bar individually, but it's counting data. This is a symmetric distribution. Most of it's in the middle, okay? And the middle of this distribution is the mean. And you can see that we've used this mu notation. That's the population mean. So this is a graph of a population distribution. And then what these marks are, is this is the standard deviation. So see this sigma here? That indicates the mean plus 1 standard deviation. And then this next bar right here is plus 2 standard deviations. And what this does for you is it gives you a visual of what 1 standard deviation does to the bulk of the data. So this is called the empirical rule. And what that rule says is that if the data is roughly symmetric, okay, and bell-shaped, the following occurs. Okay. what you get is that 34% of the data is on the right and the left of the mean within 1 standard deviation away. So this is kind of interesting because if you know that your data is roughly symmetric and bell-shaped, you can kind of predict where the data values are going to fall. This 34 plus 34 is 68. So this is saying that 68% is within 1 standard deviation of the mean. 68% of the data is within 1% standard deviation of the mean. Okay, now if I go out 2 more standard deviations, I then add all of this stuff too. Like this right here is 2 standard deviations to the left and 2 standard deviations of the right. So now I'm looking at all of this data as well. Okay, and so my percentage of data grows significantly. And what we say about data is if the data is more than 2 standard deviations away from the mean, so that means if it's out here or out here, then it's considered unusual. Okay, that's the word that we use for it. So let me write that down, and then I'm going to give you some concrete numbers and we'll do an example. So a data point is considered unusual if it is more than 2 standard deviations from the mean. Okay, so let's do an example. If we say the mean height of a population is 62 inches with a standard deviation of 6 inches, estimate the number of data points between 56 and 62 inches. Okay, so we're going to draw a picture. We're assuming for the sake of these problems that this is all symmetric and bell-shaped distributions. So let's draw one of those. Okay, we're going to go roughly like this. We'll learn more about this distribution in a later section. So for now, let's just draw that. The mean is always in the middle. So this says that the mean height, let's say we're dealing with US women or something like that. Okay, so mean height of women in the United States is 62 inches. So that means that this middle value is 62. That's our mean, and that's in the middle. So that's this value right here. Okay, that middle line. And then I've got a standard deviation of 6 inches. So that means that when I go 6 inches either way, in either direction from that mean, that's 1 standard deviation away. So what I'm going to do is I'm going to take that mean of 62 inches and I'm going to add 6. So 62 plus 6 is 68. Okay, so this right here we got because we did 62 plus 6. And then we're also going to minus 6. So this is going to be 56. And I'm getting that number because I'm going 62 minus 6. So that's 1 standard deviation away. And if we want to draw these lines, this is breaking this up like that. Okay, now we can do this again. We can do 2 standard deviations away. So let's do that. we're going to go 68 plus 6 again. This is going to be 74. Okay. This is 68 plus 6. Okay. And then we're going to go the other way from 56. So if I subtract 56 from here, I get 50. Okay. So this is going to be 56 minus 6. So you don't have to write this stuff down here. I'm just doing that for reference so that you understand how I'm calculating those numbers. So this is the distribution for the heights of these women. Now, what the empirical rule says is that we should have 34% should be within 1 standard deviation of the mean. So 34% of US women will have a height between 56 and 62 inches. And 34% of women will have a height between 62 and 68. Okay, so if I ask this question, estimate the number of data points between 56 and 62, well, that's going to be between here and here, this section right here. So I would say 34%. I guess maybe the language is a little poor because it's not the number of data sets, the percentage, let's say the percentage of data points. So we'd say 34% of the women are going to have a height between those two values. Okay, let me do a follow-up question. What if my question said, estimate the percentage of women that are between 50 and 62 inches. Okay, so now let's erase this green. Okay, and we'll do this in orange here. So I'm going to go between 50, so that's here, and 62 inches, that's here. Now, my empirical rule says 34% are in that little section right there. And then let's go up and look at this graph again. It says 13.5 are between 2 standard deviations, 1 and 2 standard deviations. So this little section is 13.5. So how many in that whole section altogether? You're just going to add those percentages together. So I'm going to go 34 plus 13.5 is how I'm getting my answer here. And I'm going to say this is 47.5% of the women are going to be between 50 inches and 62 inches. See how that kind of works? Okay, so now let's talk about this word that we defined, unusual. A question I could ask you is, if a woman is, let's say, 75 inches tall, would she be considered unusual? Okay. So all that means, unusual is a poor choice of words. She's not unusual. She's brilliant and beautiful in her own way. But what we mean by that is atypical, right? Like, so most people are in this range and she's kind of out of the range. She's taller than most people. That's what we mean about unusual. So I would go, okay, 75 inches. Let's go up to my picture. Where does that occur down here? Here's all my measurements, right? Down here, these are all my heights. This is 74. So 75 is right here. It's above 1, 2 standard deviations away from the mean. So we would say yes, because that 75 is more than 2 standard deviations away from the mean. So my answer would be yes. Okay. Now, what about 45 inches? Okay, well, let's go up to our graph. Oh, 45. I thought I was picking a different, better number. We'll do this one. 45. This lowest number is 50. So we're down here at 45. It's very unusual. It's a very short individual. Okay. So yes, also in unusual. Okay. Let me pick what I wanted to pick. What about 57 inches? Let's go up here. 57. Okay, here's 56. So 57 is right here. That's within 1 standard deviation of the mean. So that is a typical height. So I would say no, this is not unusual. Okay, so basically when I'm asking you about unusual or not, you're finding that value here on the number line and you're just figuring out how far away from the middle that is. And that's how you do those. Okay. That is it for this. You can just use these for reference. These percentages don't ever change. This, these 34s, 13s, and 2.5s, that's how they always add up. And so you can, when they're asking you to estimate percentages using the empirical rule, these are the numbers that you're using. All right, I will see you next time. Thanks for tuning in.